Here we go. So polar equations and graphs. This is going to go fairly quickly, but if you are a person who like plans on doing anything with flying or sailing or boats or navigations in military, then you may never see these again. But if that is your future, then they will probably reappear in your life. Okay. But I think it's not bad, and it's like math art. Okay. Think about it as this math. Yes. Math We're gonna call it math art. Okay. So polar coordinate system is based on a point, which is called the pole. Okay. The pole is the point. Got it? And then a ray. This is just taking things that you learned in geometry, points and rays, right? And all we're doing is turning into pole and polar axis. That's all we're doing. Changing the name. But it's essentially just a ray, correct? Just with different names. We have a pole and a polar axis. Have you ever seen the movies when the ship or the plane is navigating and they're like, "Oh no, boss, there's an iceberg or something in our path, right? Or there's something coming," and it's like that thing that's rotating. Yeah, that's what we're looking at. That's how That's what we're creating. Okay. All right. So how does polar coordinates work? Polar coordinates means that you're giving your r, which is your radius, and your theta. Okay. The difference from polar coordinates and our trig polar coordinates is that r can actually be negative now. Okay. R can actually be negative. But other than that, you have r and theta, and those are our polar coordinates. Okay. Your positive r is saying how far you are from your terminal side in that quadrant. So my terminal side in this quadrant would be right here where x is, right? And theta is how far is my radius from that line. Okay. Where it stops at is your P, your point, your polar coordinate. All right. There's a boat ahead of us at 5 to 10. Okay, which means 5 meters on the radius or whatever they're measured in. All right. So this is what I was trying to tell you, the circle thing. Got it? Okay. So when you are graphing them, you actually have a positive value on your radar on your system, and you have a negative. So if R is greater than 0, meaning positive, then you're going to be where the terminal side is. So this is my terminal side, and that's how far I am from the terminal side, right? Now, if it's negative, that means instead of moving towards this point, you're moving away from it. So you're going to be on the negative side, the opposite side of the point. Yes? Are you with me? So for example, if I'm at negative 130, right? So negative 130 means that I would find 30 degrees, right? And then I'm going to go to the opposite side of it instead of heading towards it. Okay? So what are the formulas? Oh my gosh, the formulas are the same ones we've been using all semester. Okay. They are the exact same formula, but just being used differently. Does that make sense? So, really, it is the last lecture. Here we go. So we have x equals r cosine theta because, again, anything with cosine is our x, right? We have y equals r sine theta. We have our Pythagorean, r squared equals x squared plus y squared. And then good old tangent, which is y divided by x, correct? Y divided by x, which becomes sine over cosine. Has that changed since chapter 1? Really? I wouldn't know. Really? Okay. They're all lying. So as you watch this video, please ignore them. They learned this. Okay? I promise. No, they learned. All right. So formulas haven't changed, correct? Agree? All right. So let's put it to use. So for example, here it says plot. We're going to plot each point by hand, but I've already plotted it. I thought it was going to pop up on its own. Just pretend you don't see it yet. All right. So if I have P 2, 30 degrees, the 2 represents my radius, correct? 30 degrees represents how far I am from the terminal side, correct? Got it? How far am I from the terminal side, which is your positive x-axis. So from the positive x-axis, I've only gone 30 degrees. So here I am. I'm going to draw out beep, 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 beep. That's one circle. Beep, 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 beep. That's the second circle. Why am I drawing 2 circles? Because how far out am I? 2 radius, right? I'm 2 units on the radius, and then 30 degrees. So here is where this point is located. Okay. Let's look at a better picture. Here you go. All right. So you saw my drawing by hand. Here's the drawing by computer. Okay. So the drawing by computer, you can see exactly what I said. We've gone 2 units away from the origin. And from those 2 units away from the origin, we have to be 30 degrees from the terminal side. Now, because our radius is 2, that's why we're moving towards it. If our radius was negative 2, we would be moving away from it, and that's where the point would be.
So if we're moving away from, are we going to do one with negative?
Yes, we are. The angle has nothing to do with how this dot is moving. The angle is where it starts at, and then it'll move. So let's look at a negative, okay? So let's finish this. Converting the formula. So to go from polar to rectangular, we're going to use our formulas. So we know that our x equals r cosine theta, correct? Do we know our r? Do we know our theta? Can I plug those in? Yes. So we plug them in. So we have r is 2, and we know the cosine of 30 is squared 3 over 2, because we have those memorized, right?
Yeah.
Yeah, we do. Okay.
Yeah.
And then we simplify it. Okay. Toodles doodles. Oh, thank you. So then we have the square root of 3, right? Now we're going to do y. What does y equal? R sine theta. So we're going to take r sine theta, plug in our r and our theta, and the sine of 30 is 1/2. Half of 2 is 1. So I now have my x and my y, which is what rectangular coordinates are made of. Rectangular coordinates are made of x's and y's. Do I have my x's and y's? Yes. So here's my rectangular coordinate. Okay. So sum up what we did. We plotted by hand, correct? Yes. And then we found the rectangular coordinate. Meaning that if this was an XY plane on a Cartesian plane, yes, a Cartesian plane instead of a polar plane, polar coordinates, then this will repeat.
Okay. Not bad.
Yep.
Would we ever use the r squared, x squared, y squared?
Yes, we will. All right. So someone asked for a negative example. So we're going to do a negative example. So here we have point Q, and it's located at -4, 2 pi over 3. Okay. So the first thing you're always do is start off with the angle. What is my theta? 2 pi over 3. Where is it located normally? What's here? What quadrant? Quadrant 2. So 2 pi over 3 is normally in quadrant 2, right? And so because it's a -4, instead of me moving towards it, I'm moving away from it 4 units. So my point is actually located at -4, 2 pi over 3, which is now in quadrant 4.
The rate was all the way.
Exactly. The rate goes all through. The angle's not changing because you're just following where the radius is telling you. 3/6. Well, yeah, you're just going around. Gracias. All right. Yes. So we just see how it was negative. All right, but we still start with the angle, correct? So we're still finding the angle, and then our radius is telling us if we're moving towards it or away from it. Radius challenge. All right, so now to convert from our polar form to our rectangular form, it's gonna always be the same. R cosine of theta, and then y cosine of theta. Yes? So now we have those values, plug them in, and ta-da, we have our rectangular form. So our rectangular form would be 2, -2 square root of 3. And you know it should make sense because are those values in quadrant 4? Yes. Yep. Are we good still? Questions, comments, concerns? All right. Just double checking. This one, where should I be? Yes.
That'd be in quadrant 1, and we can be in quadrant
We are in quadrant 4. Why is it in quadrant 4?
because it's the negative.
It's negative. And so, there we go.
Question again.
Hit it.
So since it's that way, we're gonna be going like this instead.
It's still in quadrant 4.
Yeah, so we'd be going.
We're still going?
We're still going.
Yep.
So like,
Still through. You have to go through the angle. Got to go through the angle and through the origin.
Okay.
Okay. It has to go through the where the angle point is and through the origin. Okay. Next, because it's 5, so we know we're in quadrant 4. Are we moving towards it or away from it? Towards it.
Okay, so yeah, that's
Make sense?
trying to visualize.
There we go. Yeah.
Okay, yeah, that makes sense.
Okay. So -pi/4 puts us in quadrant 4. Then we draw our line. Our line is going to go through it, and we are walking towards it from the origin. Negative pi over 4? 7 pi over 4. Yes, it's positive 7, which is what you can put it in to figure out where it's at.
Okay.
Okay. All right. So negative pi over 4 isn't on our unit circle, but 7 pi over 4 is on our unit circle. So what is the cosine at 7 pi over 4? Well, that's square root of 2 over 2. Same thing for our y. We're going to look at sine of 7 pi over 4, which is also square root of 2 over 2. The only difference is that it is negative. Why is it negative? Because I'm in quadrant 4. So my rectangular coordinates are listed as follows.
That makes sense.
Exactly. Remember, negative angles mean we rotate clockwise instead of counterclockwise.
So going this way now.
Yes. Not a good link, but you know.
Yeah, just to
All right. So please note that while a given point in the plane can have only one pair of rectangular coordinates, right? The same point can have an infinite number of pairs of polar coordinates. And the reason being is one, coterminal angles, right? I can rotate multiple times, right? So not only can I rotate multiple times, but I also can have the negative, which is the opposite of it. Okay. And they're going to still come down to be the same polar coordinate. All right. Same rectangular coordinates. So there's infinite polar because we can rotate. It's a circle. Does that make sense? All right. So let's talk about ways to do it. So first off, don't look at the purple yet. Look at the red. Okay. Don't look at the purple. Look at the red. So starting off here, if it asks you for polar coordinates, the easiest way to do it is to focus on the smallest three that you can create. Okay. The smallest three that I can create come from taking your original angle. So same radius, taking your original angle and subtracting 360 from it. That'll give you 1. Does that make sense? Because I now went clockwise the other way around, right? Okay. The next one would be finding the opposite radius. So the opposite radius is that instead of my radius being positive, it is now negative, and it's going to be across from it, which means I only go 180 instead of 360. Okay. And then the last one comes from finding its coterminal by adding 360 to that. Okay. So let's do it all together in math. Ready? So our given R is 3 and our initial theta is 140. Okay. So to find the first one, to get our 140, we're going to subtract 360. So when I subtract 360, I end up with negative 220. So these are my two smallest positive radius values. Well, yeah, in a sense, between negative 360 and positive 360. Okay, so these are my two. And then to find the next one, I'm going to find their negatives. So to find the negatives of them, this one, the negative means I'm adding 180 because I'm just crossing over, correct? So I add 180. So negative 220 plus 180 is going to put me at the 320. I'm sorry, it's going to put me at negative 40. I don't know how I said that loud. I wrote it down correctly right here. And then to find my other value close to 360, all I'm going to do is from this angle, rotate, and it's going to be a full rotation of 360. So the red is what we did, and then the purple is an example of following it from beginning to end. Okay, so then we come down to all three of our polar coordinates. So when you're giving navigational, it's important when they're saying, I'm going 3, negative 220. If I'm going 3, negative 220, where is that placing me at? Which direction, how far, turns, rotations, on all that. But ultimately, you're heading to the same location. You're just maybe going around avoiding something, or it's not a straight shot, or whatever it may be. I'm not pro or expert in that field of that career field. So, but I can tell you how to find them. All right. So again, the red is what we're following. Okay. Same radius, opposite radius steps, and therefore you can find 3 of the ones that correspond. Okay. So looking at it, so here, this one, 3 and 140. So 3 and 140 is going to find its opposite. It's going to become -3. And then in this quadrant, all I did was, what do you call it? Just got a brain fart. The distance from the terminal side. So then this is 40 degrees from here. This is 40 degrees from here, which is why it's at -140. But it's negative. All right. So next is 2 pairs of polar coordinates for the point with rectangular coordinates. So now we're working backwards. Okay. And we're going to find 2 pairs with the same one. So we're going to work backwards to find those 2 pairs. The first thing that we're going to do is figure out what is the theta. Okay. Can I find theta from just x's and y's? Huh? Yes. How do I find theta from x and y?
Oh, tan.
Tan. I use tan. I want you to use tan. That's exactly what I want you to do. So we know that our angle is going to be in quadrant number 2, correct? So our angle is quadrant number 2 because it's -1, 1. However, we need to find our theta. Now, this is an easy one that we can use from our unit circle, correct? So we know that tan theta equals 1 over -1 is -1. The only angle that's going to give us a tan of -1 is going to be 135 because we're in quadrant number 2 and that's where our 45 reference angle is, correct? Now, if you didn't have it on the unit circle, let me show you what you would have to do on your calculator. So here's my calculator. I'm going to make sure that it's in degree mode because this problem involves degrees. Yes.
Is our final on Monday?
It is. It has to be so I can submit your grades by Wednesday.
I was asking because in the syllabus it said Tuesday, but then I remember that Mondays and 8
Yeah. Why? Uh-huh.
I have AP testing all day.
You can take yours after, but for
Okay,
like
so
Grace, they have to take theirs on Monday so I can have their grades submitted. Yeah. Now
So
you have
great.
flexibility. Huh?
Great.
That's why you're taking your test on Monday. Please excuse the discussion of these real rude children.
Oh,
All right. Here we go.
I'm
In the middle of me teaching.
just worried about
All right.
grades.
Yeah, final.
Oh, that was interruption.
See, now
I
you're
was teaching you how to
interrupting.
find tan inverse.
So
All right. Anyways, tan inverse of -1. So when I find tan inverse of -1, notice that it's going to give me -45. That's because inverse tan only gives you values in quadrant 1 and in quadrant 4. Okay. So therefore, I have to add 180 to it to find its value in quadrant number 2. So when I add the 180, it will then give me the value of it in quadrant number 2. Make sense? Okay. So, but this one we should have known because it's on our unit circle. We should know that I hope so at this point that we know this. Okay. But just in case you forget, then that's what the tan inverse in your calculators. Okay. All right. So now we have our theta. After we find our theta, we need to find our radius, our r. Okay. R squared does what? What does r squared equal? R squared equals x squared plus y squared. And then we take the square root. So can we find our r? Yes. So we find our r by taking the square root of that. And so now we have that r equals square root of 2. Okay. So from there, now can I write this as a polar coordinate? I surely can. I have my r and I have my theta. So therefore my polar coordinate is square root of 2, 135, and negative square root of 2, 315. Okay, that's because this line, it goes through here, right? It's going to produce the same thing. It's straight. Pretend that it's straight. You see it. Okay, the -2 side would be over here. And this would put me at 315, which is the 45-degree reference angle in quadrant number 4. Okay, and those would be our two pairs. Okay, so how do you know if you're doing this correctly? If you were to go back through and use r cosine theta and r sine theta with either one of these values, it should take you back to -1 and 1 for both. If not, then you did something wrong. So like, because these are all their own separate ones. So you would do it for this one to find the x and the y, and you would do it for this one to find your x and your y.
Question.
And they both will take you back to that. Yes.
When we're solving backwards, are they always gonna have two? Or is it...
They may ask you for 2, they may ask you for 1, and they ask you for a positive radius.
Okay,
Yeah.
okay, yeah, just making sure.
Yeah. But the 2 is the easiest in my opinion, because all you're doing is using the reference angles to find
So
the
it's
other.
just across.
The cross. All right. Questions about working backwards? Doable?
Yes.
All right. All right. So up next, an equation in which r and theta are variables is a polar equation. Okay. So our polar equations, we're going to first start off with one that should look familiar to you. If I have ax plus by equals c, way back in algebra 1, what type of function did this represent? This is terrible, guys. What'd you say? Thank you. Thank you. Someone gave me hope. Linear. Yes, you did. No. Ax plus by equals c is a linear model, right? That's when we're in our Cartesian model, our rectangular plane. But we're not in a rectangular plane, we're in a polar, okay? So when you see something in the format of ax plus by equals c and polar, it means a little different, okay? So let's explain what it means in terms of polar, all right? So for ax plus by, we're going to substitute in for x and y. So when we substitute in for x and y, that's our r cosine theta and our r sine theta, correct? Because that's what x and y represent. Okay, once I do that, I can factor out r because they both have an r in each term. And the goal here is to get r by itself. Your polar equation is defined by r. So our goal here is to get r by itself. So what would I need to do to get r by itself? Yeah, divide. There we go. We're going to divide. We're going to divide by that entire binomial of a cosine theta plus b sine theta. So our general form going from a linear model to a polar model would be r equals c divided by a cosine theta plus b sine theta. To the polar. That's, yep. To the general form or polar equation of a line. Okay, so this is our polar equation of a line.
I hate whoever didn't give me stuff.
Well, then you want ships and planes to crash into each other.
I could give me the ship or a plane.
Didn't you just ride a plane not too long ago?
Well, that wasn't by choice.
Well, but you did, so I don't know what to tell you. Okay, so
Could have, bro.
okay, that's a long drive. But anyways, polar equation. Now we're gonna talk about circle. So we did linear. Now we're gonna do a circle equation. Okay. So do y'all remember the circle formula? Circle formula is x squared plus y squared equals your radius squared. But here they used a for the radius. So this is our circle formula from geometry, from beginning of college algebra. This is the circle formula. This is a circle centered at the origin, correct? Okay. So it's a circle centered at the origin. And then your a squared is your radius, how far out it's going to go from the origin. Do y'all remember that? All right, so we're going to substitute in what we know. We know that r squared is our a squared, correct? So your r squared is your a squared. So whatever your a squared is, that becomes your r squared. So therefore, your general form for a circle in polar equation is just whatever your a is, the square root of your a, plus or minus, okay? Because it's plus or minus, that means you have to put it into the graph. Not once, but twice. Once as a positive and once as a negative. Okay, so we've talked about linear and we talked about circles. Now, for each of this rectangular equations, we're going to put it in terms of a polar equation, and then we're going to sketch the graph. We're actually going to use the calculator to sketch the graph. Okay, so but the first thing we need to do is start substituting and converting. Okay, so right now we have y equals x minus 3. Before you get started, your x and your y have to be on the same side, and your x has to be positive, okay? Because that's standard form of a linear equation. So what do I need to do to make that happen? You could do that. You can add 3 and subtract y. You can minus x and divide by -1. Does it matter which way you do it?
Either way, it's gonna come out to the
Either
same
way,
thing.
it's going to come out to the same thing. I just want to make sure we're all on the same page, okay? So we're going to make sure that we rewrite it. And then once we rewrite it as however you choose, as x minus y equals 3 is the end game, correct?
Yes.
We're then going to we're going to substitute in what does x represent? X is what? R cosine theta. What does y represent? R sine theta, and we plug those in. Again, your goal here is to get your R by itself. So to get R by itself, we're going to divide this whole binomial. Agreed? All right, now we're going to graph it. So let's go to our handy dandy calculator. So to graph this using technology, your calculator has to be in polar mode, okay? So I'm going to go to mode, and I'm going to go to, it doesn't matter if it's in radian and degrees. A lot of calculators only work in radians, but it really doesn't matter. Mine was in degrees, and it's going to graph it just fine. But if it bothers you, you can convert it. The main thing is you're going to go from function to polar. So we're going to go to polar and turn on polar. That's what's important. Yes, we're turning on polar. Okay. Once you turn on polar, when you hit y equals, you'll notice that it now says r equals. Yep. Do you see your r now? And now we can type what r equals. Well, r equals 3 divided by cosine theta minus sine theta. So we're going to type in 3 divided by, you can actually do the fraction. I cannot. So since I can't, I have to use parentheses to get my point across. So I have cosine. Notice that when you press the variable button, it's going to automatically make it a theta minus sine theta. Okay. Now we're going to graph it. So when I hit graph, it's going to, mine is really little because I need to fix my window. So I'm going to change my zoom. I'm going to do zoom square. Huh? Let's do zoom fit. We're going to change my little setting here, zoom fit, and then it should graph a line after I change my settings to zoom fit. Ta-da, there's a line. It's been graphed. The reason why I like to do zoom fit is because it adjusts my X values for me. And then from there, I can go in and change out the. Once you do, just click the variable button that where X is, it'll automatically make it a theta because you're in polar mode. That's why it's called your variable button. And a lot of times I'll just call it X. And I'm like, no, it's a variable button. Because it changes based on whatever your mode is. Yeah. Oh, so you didn't do step 1.
No, I did do it. It's insane.
Suspicious, Grace. So how you zoom in and out is going to affect it. I just do zoom fit most of the time. I'm just showing you all the different things. So I don't have to adjust it. I'm just going to hit zoom fit, and zoom fit will do the rest for me. So do you see your line? Did I graph it in polar form? Yes. All right. So let's talk about what it looks like with the right. Because I hit zoom fit. I went to zoom and then fit. All right. So this is what it looks like. So side by side.
Why does mine?
Just give up, bro. Just give up, bro.
What'd you write?
Just
Did
give
you
up.
do? What did you do, bro? I don't know what you typed in, Greg.
Type that in.
Yes. You have it dividing by cosine and then subtracting sine. That's why. Parentheses are important. Or you can just make the fraction bar like I told you, you can recalculate.
I mean,
On your calculator, you press alpha and then the button next to it, the variable button. And you can make a fraction.
You know, it would be a lot easier if we could use the blue.
It'll be.
Ching.
Oh yeah.
We don't have them.
The blue. We have them.
Oh, I have them.
Yeah.
The blue calculators I'm telling you right now are so much easier.
No,
Do
yeah.
you have one?
No, y'all have.
Yeah.
Oh well, here we go. This is what we got. All right, so do you see the difference between the polar and the
Yeah.
rectangular? Yes? All right, how do you feel? Doable?
So there's not any difference other than just what it looks like. They graph
It's just where it's graphed at. Yeah.
where it's from.
Like how it'll look as far as it's the same. So this is like by hand on a polar coordinate, on a polar grid, and then this is it on a rectangular plane. That's it. They're the same. These are equivalent. Just depending on what you're looking at. Okay. All right, next. This time, this is an example of a circle. X squared plus y squared tells me that I'm dealing with a circle. Because I'm dealing with a circle, all that matters is the constant. Okay? Since it's a circle, all that matters is the constant when you're going to polar form. All right?
Just plus or minus
What's square root of 4?
square root of 4 is 2.
2. So all that matters is plus or minus 2. And that's all we're going to put in. So when we graph it, we're going to graph r equals 2. And we're going to graph r equals negative 2. You have to graph both in order for it to make the circle. So I'm going to go to y equals. And I'm going to graph 2. And I'm going to graph negative 2. I'm going to go to zoom. And I'm going to go to zoom square. It's thinking. Not being my friend. Or not.
It's a circle.
Oh.
It's a circle.
It's a circle. It's a circle.
Wow.
It's a circle.
Wow.
Oh yeah.
Wow. Looks like Miss Jones' circles is crazy.
This is a football.
You know what? I feel like someone's being a hater right now. Look, if you hit square, it'll make it more of a circle. Like if you go zoom square. Square.
Five.
Was longer. Let's see, that's a little better.
Is that a little better? Makes you happier? Okay.
But it's the same thing.
Yes. All right. Questions, comments, concerns. Set. Notice that it says coincide, which means that they end up lying on top of each other. Okay. Yes. I don't know. Enough.
So I don't want to miss
Oh,
what you have.
a little. We have a lot more to go. There's 33 in total. I don't know where we're at. We're only on 18.
Isn't there 33?
It's
I
fine,
said-
I'll wait.
All right. So questions, comments, concerns. Okay, cool. All right. Now we're going to get to the fun. Okay. This is not a line nor a circle. Okay. It's called I'm always going to butcher this word, but it's called a cardioid.
What?
A cardioid. Cardioid. Okay. I call it the plum. Okay. But it's called a cardioid. All right. So the cardioid means that you have your R equals cosine or sine plus or minus a value.
Oh,
Okay. So a cardioid means that you have cosine or sine plus or minus a value. In this case, we have 1 plus cosine theta. Okay. When it's cosine, your cardioid is going to be focused on the x-axis. Okay. When it's sine, your cardioid is going to be focused on the y-axis. Does that make sense? All right. So cosine means that our cardioid is going to be focused on the x-axis. So when we graph this in the calculator, you can talk to how it's going to build up. If you were having to do this by hand, what you would do is make a table of values, plot those points. The table of value is usually from 0 to 360. So you find the values. So the cosine at 0 is 1, the sine, cosine, at all these values. And then you add or subtract whatever it's telling you to, right? So in this case, it says to add 1. So I would add 1 to all those values, and then I would plot those points, okay? From plotting those points, what's going to end up happening is it ends up looking like this. Okay, and it connects because 0 and 360 are the same, so you come back to where you started. Does that make sense? Okay, I think it looks like a plum. I don't know why. It looks like a plum to me. I don't know. I also like plums. And yeah, but you can call it a peach if you want.
Looks like that one bug. From the
11th grade me has called it a plum for a while. For like 2
Miss
decades.
Jones has also said very interesting acronyms as well.
First off, it is what it is. You remember things though. So here's our cardioids. Okay. Now when you graph it in the calculator, you may not see I'm going to show you in the calculator. it's important for your adjustment to your window. Otherwise, you may not see the little curvature in. Does that make sense? So when you're putting in the calculator, pay attention to what your window is. So for example, I wouldn't change my min, my max, or my step or anything, but I would change my minimum and maximum. The reason why I would say I would change those values is just because if it's too far out, you won't see that circle. And on your y-axis, no value is going to be that high. Because when you looked at our chart, did we have values that high going in? No, we did not. So I would pay attention to that. But once you find those values, this is where you're at. So you're going around and around and coming back. Then it'll graph it correctly. So all you're doing is typing in is the 1 plus cosine theta. So let me open my handy dandy calculator. Here's Sylvie. She's on. So I'm going to go to y equals, and we're typing in 1 plus cosine theta. I'm going to go to my window. And my window right now, it's set up pretty high. If I want to try to like narrow some of it down or see what happens, I can hit zoom and I can do standard, zoom standard. So you see, I said that this is the standard form. It's kind of hard to be able to see that. So when I said it may get a little weird, I can do zoom square and see if it helps me, which is 5. It got a little more circular, a little more plumped, but I still can't really see the curvature of it, which is why it's important for me to go ahead and zoom in. So when I zoom in on those values, that's why that negative, sometimes I just use the whole numbers, but it doesn't really matter. I'm not going to change the scale, but I am zooming in on my values. So that when I graph it, notice now I can see the fullness of it, the beauty of it. Yes? How do we feel? Doable? Okay. Unless you want to learn and make a table. And how to identify what they are. Yep. All right, here you go, Lily Rose. This is the Rose model, okay? The Rose model means that you have a double angle situation. So it's going to be, well, or a multiple theta situation. It can be double, triple, quadruple, but the rose means that you are duplicating that theta, okay? So when this happens, all you're doing is taking whatever theta value you have, you're doubling that theta value and then finding the cosine of that value. And then if there is a coefficient on the outside, then you're multiplying by that coefficient value, all right? When you're plugging in the calculator, it's just doing all that for you. Does that make sense? Okay. So the calculator will do that all for you, but you could create it by hand and find said values of what your radius or your R is going to be at those points. But when you graph it, this is what it looks like. I'm gonna create a flower. Okay, so when you have it, this is a 4-level rose, a 4-leaf rose, and it's a 4-leaf rose because it's a double. When we're gonna look at the summary chart, but when you have two, an even coefficient of your theta, it's gonna create a duplicate amount of petals. Okay, so notice that I have 2, right? So that means that it's gonna create 4 petals on my rose. If it happened 4, then it would create 8 petals. Okay. Because it has 16.
Oh, dang, yeah.
Because it all have 16. So if it has 8, then you're going to now have 16. Okay. All right. So this is our 4-leaf rose. So our 4-leaf rose is created from starting to finish and going around. So
changing the A.
So changing the A is the length of the rose. So how far your petals go out. So my petals are going out 3 units from the origin. Does that make sense? Why are you doing that? Okay. And she giggled about it. There you go. All right. I told y'all to think of this as art today. Did I not?
I don't hate it.
Did I tell you not to think of it as art?
It's the only time.
What a way to end, right?
The only time I've ever paid attention.
It is not. Please,
one time
they are trolling me on this video. Ignore them.
Finally teaching us, and now it's interesting.
There's all these other videos of proof that they're lying. All right. So, questions about the rose. We're good? All right. Now we're going to look at a lemniscate. I just called it a lemon in high school because lemniscate was not working in my brain.
How?
Lemniscate.
Lemon.
Lemniscate. 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 Lemniscate.
Lemon.
Lemon. Lemon.
So,
We're gonna call it a lemon.
on the notes, there's that one and what the cardboard.
The cardioid was the first one.
Yeah,
Yeah. The plum.
yeah. No, it's because when I was doing the notes, it just says circles, that one, and then line of ponds, ring ponds, whatever.
Yeah, cardioids are considered circles.
Oh, I see.
Yeah.
Okay.
Cardioids are considered circles.
That
Alright.
makes sense.
So we're at r squared equals cosine 2 theta. When you have a lemniscate, that means your r has been squared. Okay, that's how you know you have a lemon. Oh no. Okay. So you have to take the square root, which means that in order to make the graph, you have to put in two models. Does that make sense? A positive and a negative, because anytime we take the square root of anything, it's going to produce a positive and a negative. Okay. So for example, here, this is what the table would look like. So if you were to find the values, the cosine of double the angle, you would have the plus and minus of each value. Okay. So that's what ends up happening. So when you graph it, it's going to end up looking like this. Okay.
Cool.
The cosine one is going to be centered around your x-axis. Okay. Cosine is centered around your x-axis, whereas sine is going to be diagonally through your origin.
Why is mine not?
I don't know. Are you still in polar? Should be. Okay. Let me look. So when I go to screen, I'm going to go over here, my graph. I'm going to open her. Hey, girl, hey. I'm going to go to y equals, which is right now r equals. And I'm going to put in square root of cosine, cosine 2 theta. And then I'm going to put in negative square root of cosine 2 theta. And I'm going to hit graph. I don't know. Yeah. Little bow tie. Someone said it looked like Spider-Man. The Cartesian with the polar.
Yeah. I can see
They
it.
said it looked like Spider-Man. It wasn't me. Huh? You get the vision.
I can see
All right. But do you see the two lemons?
Yes.
I know you see two lemons. Okay, but do you see the two lemons?
Yes.
That's to help you remember the name of it though. Okay. It's supposed to help you remember. Okay. All right. So when you graph it again, make sure you're putting in both. And your window doesn't have to be very large because these values aren't going to be very large. Okay. So notice that my window on here for the close-up view is simply -1 to 1 on the y-axis and -1.5 to 1.5 on the x-axis. Yes. All right. Okay. Next is called the spiral of Archimedes. Okay. So this one.
Yes.
This one is just only when you're given the theta. Okay. So when you're given the theta, and you're graphing the theta,
In
it's
radians.
going to, yes. Notice that theta is measured in radians for this one to work. Okay. Specified in radians. Okay. When you're given the theta, because it's infinite and it's looping, what's going to end up happening is if you're taking your radian values and all you're doing, theta values, and all you're doing is doubling them, that can be an infinite situation, right? There you go. But this one, it's a very limited one of it. So this was 2 theta, and this is what it looks like. Nope, you only do 1.
How do you guys work it out?
So on the calculator, you want to make sure that you I'm gonna go here. I'm gonna clear. All you're simply putting in is 2 theta. So you're gonna put in 2 theta. And then I'm gonna go ahead and change my window. I'm just gonna go to zoom and go to standard so that it'll automatically be at 10. Did not put the 10. Oh, I'm not in radians. I'm not. Is the calculator tripping? Oh, it's at 360. My theta is in pi. Hold on. I'm going to put it at 2 pi. 2 pi. I'm going to not count by that. I'll just count by pi. And then,
You should have a class where we learn how to.
what am I doing wrong?
This goes up.
I'm just gonna do zoom fit.
Oh,
Oh, that's even worse.
oh.
I didn't change my mode. My mode is right.
That's what I'm talking about, miss. This is just, if I got that spiral.
This is what it's supposed to look like in our handy dandy calculator. Well, at least you got that. Old Sylvie over here is struggling. Sylvie got me an angle. Yeah. Huh.
If it doesn't
Hold
have
on.
this one, then we get to use it.
That's not what I said.
I have like a fair like this is like a fair like that.
Strong.
That is just weird. Nice try.
That's one question we get right.
It does not want us to be great. Yeah, on the Y, I graphed it exactly. Zoom. Standard. There. That's all it's gonna give me. Interesting. I wonder if it doesn't show you have to graph. Don't do that. I know, look at that art, but don't do that. I'll just put the negative in to see what'll happen. You know, playing with it. Okay, but this is the graph. I don't know why it's doing that, but this is what our goal is, and it's so weird. I don't think I have it on there, so don't worry about it. All right. For the part of our art learning.
I don't hate it.
The main ones we will be. All right, so here it says convert to rectangular, so going backwards. So can we go backwards? The answer is yes. Okay, we have to be able to go backwards. So here we go. If we can go backwards, then we are golden. The main thing here is you want to get the 4 by itself. So before you get started, what are you going to do? And then you get the constant by itself. I'm going to multiply. So I'm going to multiply both sides by 1 plus sine theta, right? When I multiply by 1 plus sine theta, on the left-hand side, I'm left with r plus r sine theta equals 4. What does r sine theta equal?
Well,
R sine theta equals what variable? Y. R sine theta equals y. R sine theta equals y, and r equals the square root of x squared plus y squared. Because your whole job of getting rectangular coordinates is to get everything in terms of x's and y's. Now, just like any other time, when you're writing a rectangular coordinate form, your goal is to get y by itself. So in order to get y by itself, I have to get rid of a radical. In order to get rid of this radical, it has to be isolated. So if I want to isolate my radical, what am I going to have to do with the y? Subtract it. So I subtract the y. After I subtract the y, how do you cancel out or undo a radical? You just square it. I'm going to take the square. What I do to one side, I do to the other. So now my radical is gone, and I'm left with 4 minus y squared. What does 4 minus y squared mean?
What do you mean? Like
What? No, what does it mean? What does it mean I have? If I have 4 minus y squared, I have 2 of them, right? So I have to use multiple distribution, or AKA what method to get rid of that? FOIL.
Okay,
Yes.
I was right.
Multiple distribution or the FOIL method. So when I expand it using FOIL, I'm down to 16 minus 8y plus y squared. I have a y squared on the left side and a y squared on the right side. So what happens to y squared? It cancels. So I'm just left with x squared minus 16 equals negative 8y. What is the last step I need to take to get y by itself? Divide by negative 8. So my rectangular form would be y equals negative 1/8 x squared plus 2. So this is where it started at. I tried, but it started getting weird. So I was like, I'm gonna be a little weird.
You drew a peach. Or lips. I
Or an
can see
island.
lips. I see lips.
Okay, guys, pretend it's a square and continue.
I don't think you've ever.
It's a rectangular box around our rectangular
That
coordinates.
is no rectangle nor square. That's more of a circle than anything.
All right, what shape would that make? Yes, you do.
Oh, you're talking about that one?
What is it? What kind of parabola?
Upside.
An upside down, a negative parabola. Bam.
Wow.
We
More
did it.
shapes.
We did it. Yay. Okay. All right, summary. Here we go. So these are your circles and your lemon skates. Your circles are AKA your I can't talk. Cardioids. Okay. So the shape and how much curve is on it. Again, if it's a circle, a regular circle, with cosine, so a cosine theta, it's right there. A sine theta is centered around the y-axis, which makes sense because sine is focused on who? Y. If you have a lemniscate, for sine, it's going to be diagonally through the origin. If you have a cosine lemniscate, it's going to be horizontally lined with the x-axis. Okay, so let's dive a little bit more into our limicons, which all AKA are cardioid. Yeah, this is the one that's cardioid. I don't know. Yes, yes. They also are called your cardioids, but they can be called limicons. They're the same thing. Okay. Someone said it helps you think that they look like a lemon, like a pea. But either way, this is when you're adding or subtracting to the circle. Does that make sense? So the circle is just normally, look, let's go back. So circles are just going to be a cosine theta or a sine theta, right? Once you add or subtract, so you add a second term onto it, that's what changes the shape of your circle. Okay. So changing the shape of your circle, there's rules to follow. If the ratio between your A and your B is less than 1, you're going to have a vertical upside down situation. If the ratio between your A and your B equals 1, that's where we had got this horizontal plum shape looking. If your ratio of your A and your B is between 1 and 2, it's going to be a little smaller plum. And if the ratio of your A and your B is greater than or equal to, it's going to be a circle with a little bit of a flat bottom. And that's how you classify your polar equations. Mm-hmm. And you survive. I'm just saying you survived these. Yeah, we have really what?
I'm sorry to be done. Like, you can't act like we're wrapping up.
It was one more. It's the rows, which we already talked about, right? So we talked about the petals. So through our notes, we talked about when you have the even petals. Now, when you have an odd end, so when it's an odd number of an odd coefficient on your theta, it is what it is. So if it's a 3, then there's 3 petals. If it's a 5, then it's going to be 5 petals. If it's 7, it only doubles if it's even. Okay. It only is doubling if it's even. If it's an odd coefficient on your theta, then it's going to just be what it is. Capiche? All right. And then the A again represents the what? What did we say the A was?
Yeah.
The length.
Yeah.
The length of the petal. Okay. Or the leaves or whatever you want to call it. I don't think a leaf and a petal is that much different. So whatever you want to call it. All right. And that completes our last and final unit section of 1316. You survived with all your drama, dramatics, and trolling, and